All right, let's get started. And today we will continue to discuss about database design. Um, Last time we have been discussing about the process by which databases are designed. It starts with the requirement analysis, then you do the conceptual design, afterwards a schema normalization, and finally physical tuning. So the last time we have started discussing about the conceptual design stage. And in that stage, you use tools such as entity relationship diagrams in order to model at a high level of abstraction what data you want to store in the database. Now, the last time we have already started discussing about entity relationship diagrams, and we have seen a couple of visual representations for different elements, for different aspects of your database. We've started discussing about entities, which can be persons or things. It's a very generic term, and they can be associated with attributes. As a little reminder, this is how we represent them: entities as rectangles, and attributes as ovals that are connected. Then we have discussed about relationships which essentially connect multiple entities, and we represent them as diamonds in those diagrams, like you see here, for instance. So here, those are binary relationships because they connect two entities. All right. We can also have ternary relationships connecting three entities, or even relationships that connect more than three entities. There is some differences in terms of the semantics, in terms of what you can model with them, and we have quickly discussed about that last time. We have also seen that we can classify those relationships further by introducing constraints. In particular, we have seen the participation constraint, which essentially means that an entity needs to be related according to a specific relationship with at least one other entity. And the at most one constraint essentially means that one entity can be related to at most one other entity in a binary relationship, or for instance, in a ternary relationship, it can be related to at most one combination of entities. So we represent participation constraints by very thick lines in the diagram, and at most one constraints are represented as arrows in the diagram. So this is an example here. For instance, on the right-hand side of the slide, we have the example that students, they have one favorite course, and here you see the combination of a participation constraint and an at most one constraint, because here we have a thick line and an arrow, meaning that each student is linked to exactly one course that is the favorite of the student. So this is how far we got last time. And then we have started discussing about, subclasses. So maybe I should also very quickly remind those two features. So here we have also quickly discussed about the fact that we can associate relationships with attributes, and also we can associate relationships with roles that we assign to the different entities that appear within a relationship, which is required in cases where a relationship connects entities of the same type. And perhaps here, let's have a quick look at this example again. So here we have the entity of type employee, and there is a supervisor's relationships between different employees, which is associated with an attribute. That's the start time of the supervisor's relationship. So starting from when was this employee managed by this other employee. And here we have a relationship that connects employees together. So we are connecting entities of the same type. And then it becomes important to assign those entities to roles. And here you see those roles are modeled as labels on the lines connecting the relationship to the entity type. We have the supervisor role and we have the supervised role. There's also constraint in here, as you see based on the arrow. So for the supervised employee, we can have at most one such relationship. So each employee can be supervised by at most one supervisor. So that is a little reminder of the things that we have seen. And now in the following, we're going to see more features of entity relationship diagrams. And later, we will see how we can translate those entity relationship diagrams into actual SQL commands or into relation schemata. So one feature that entity relationship diagrams allow to model is subclasses, which is something that most of you might already be familiar with from object-oriented languages. And if you introduce subclasses in your diagram, you essentially reduce the amount of drawing that you need to do, because the subclasses automatically inherit certain things from the parent class, such as the attributes and also the relationships. So if you say that one entity type is a subclass of another entity type, then you save yourself the work of having to redraw all the attributes that are in common between a subclass and a superclass. We represent those subclasses as triangles. Those triangles, they're connected to the superclass and to the subclass, and typically still have some label inside of them. For instance, there is a label. We only support, we don't support multiple inheritance. So if you only consider those subclassing relationships between entity types, then that will form a tree. To make things more concrete, here is an example. And let's, for instance, assume that we have a university database. So we have employees, and then perhaps there's different classes of employees, such as the instructors. And here the employee already has a couple of attributes. So first of all, we have the net ID. And the net ID is a key, which you recognize because it is underlined. We also have the name attribute. And those employees are also in a supervisor's relationship with each other, which we have seen in the previous example. And now we essentially introduce a specific class of employees, which is the instructors. And we can represent that using the subclassing relationship. So here you have the is a relationship, and it connects the employee to the instructor. And the instructor is thereby classified also as an employee. So it will automatically inherit the attributes net ID and name, even though you don't see them here explicitly in the diagram. It also adds a new attribute, which is the number of courses, which only makes sense for instructors, but not for other employees. And it also adds a new relationship, which is the teacher's relationship, which connects an instructor to the courses that are taught by this person. So here we have added a relationship and a new attribute that only makes sense for this specific subclass of entities. Now, another commonly used feature in the context of entity relationship diagrams, this is weak entities. And a weak entity is generally an entity that cannot really stand all by itself. It's always dependent on another entity, and we call that other entity the owner entity. So more precisely, the weak entity will have some primary key, which essentially only becomes unique if you combine it with the primary key of the owning entity. And in order to indicate which is the owning entity, we have to connect the weak entity with a relationship to the owner entity, and it has to be a specific type of relationship. The weak entity needs to be connected by an exactly one relationship to the owning entity. And to make things more concrete, let's just look at an example. So here, for instance, assume that we have an entity type homework, which stores an attribute that is the homework number. And the homework number, all taken by itself, is not necessarily unique, because a homework could belong to different courses. So there will be a homework one from multiple lectures. So as long as you only store the homework number, it doesn't uniquely identify the entity. And this is indicated by underlining the homework number here by this dashed line. So this is different from the non-dashed line that we use for primary keys. So here the homework with the partial key homework number is connected via the belongs to relationship to the courses table, which has the course ID primary key. And now if you take both of them together, if you take the homework number and the course ID together, then you get a unique identifier for one specific homework. So that is the semantics of weak entities. They don't have a really unique key, but if you combine their key with the key of the owning entity, then you get a unique key. And here in this example, the weak entity is the homeworks. Another important concept in the context of entity relationship diagrams is aggregation. And that essentially models a relationship of a relationship. So if a relationship between entities exists, then you can add some additional information about that. We represent this by putting the first relationship into a dashed rectangle, which contains the relationship and the associated entities. And then you connect this dashed rectangle with other items. This is how it looks like. So here, for instance, we could have a situation in which we have departments associated with a department ID, which sponsor projects, and this sponsoring relationship is associated with a since attribute, meaning this is the point in time at which the sponsoring started. And then we have employees that monitor this sponsoring relationship, making sure that everything is accounted properly, for instance. So this is why we have this aggregation relationship. So we have put the first relationship, the sponsoring relationship, into a dashed rectangle. And now we connect that relationship with a corresponding employees that monitor the sponsoring relationship, right? So here we have the monitors relationship, which is relationship connecting employee entities to sponsoring relationships. So that is aggregation. And perhaps to clarify things, I mean, in this situation, you could also imagine that we are connecting perhaps 3 entities, the employees, the departments, and the projects. Does anyone have a suggestion about reasons why we would prefer the aggregation in some cases over those ternary relationships? Okay, all right. So there's the proposition that the department might be monitoring multiple projects. And we don't want to repeat the employee every time when we are drawing. So you have multiple propositions coming in. So here the monitors relationship connects one specific employee with one specific combination, essentially, between department and project. if you think, for instance, about the constraints that I could add here. So this all goes into the right direction already. I mean, there's many reasons, so there's multiple correct replies. And specifically thinking about a case where I want to introduce constraints on those relationships. If you imagine the same thing, if you imagine instead of this, a ternary relationship between employees, departments, and a project. Okay, yes, very good. So now, yes. So here the proposition is to look at those constraints on relationships that we have seen. Here we have the at least one relationship mentioned, and there's also the participation constraint mentioned. So here, for instance, what I could model would be something like making sure that each combination of a department and project, where the department sponsors the project, is monitored by someone. So I could express this by a participation constraint that connects the sponsor's relationship to the monitor's relationship. Now, on the other side, if you have a ternary relationship, you might be able to express that specific departments or specific projects can get monitored, but you cannot really express that the combination of a department and a project needs to get monitored. And that is only one example. So here we could have multiple constraints that we can model when having two separate relations, but we cannot model them when only having one ternary relationship. So there's a lot of subtleties about which model, which entity relationship diagram you choose in order to model a certain situation. And you have to be careful that whatever representation you choose really allows you to model all the constraints that you want to add. Okay, so very good propositions here. All right. So in general, you have a couple of design choices. Now here we have already discussed aggregation versus ternary relationships. And one thing that you also often can choose is whether you model certain things either by introducing new entities or by adding attributes to an existing entity. For instance, if you think about something like an address, let me quickly move something here. If you think, for instance, about an address, then you can either consider introducing an address entity, or you can consider this rather as an attribute of an existing entity, like of an employee. The first thing to consider is whether the entity, for instance, the employee, can be associated with multiple addresses. Now, attributes in entity relationship diagrams, they must have simple types. They must have, for instance, string or integer types. In each case, they cannot store a set of values. They can only store a single value. So if you want to model something like one employee could have multiple addresses, then you have to model this by an entity as opposed to an attribute, because those attributes, they couldn't store a set of addresses. And also, if you want to structure the address further, so often like an address is structured into multiple fields, you might have the street number, the city, and so on. If you want to represent that structure, then you also have to model it by introducing a new address entity, because then you can model those different components as attributes of the address entity. So those are some of the things to consider when choosing between entities and attributes in your model. Here we have an example. What we're modeling here is the works for relationship between employees and departments. And this works for relationship is associated with two attributes, the from and the to attribute. Can anyone tell me what might be wrong with this representation? Can you imagine a situation that you would like to model, but cannot model with this representation? So remove the question so you can see the diagram better. The question is, can anyone tell me what might be wrong with this representation? Okay, very good. And here there's exactly the point that I was looking for. Great. So the thing is this, one employee might work repeatedly for the same department. Maybe that person worked for a different department for a while and then is coming back to the first department, or even worked for a different company for a while and then is coming back to the department. And that means that I want to be able to associate one employee with multiple time periods during which the employee worked for one specific department. Now, in this representation, the from and the to attributes, they have a one value for each combination of an employee and a department, right? So here the works for relationship connects one employee and one department. And here we can associate works for with from and to, but we can only pick one value for from and to for one specific combination of employment and of employee and department. So if you want to resolve that, a better model would be the one that you see here. So here we add a new entity type, the time period of the employment, and then we model the works for relationship as a ternary relationship connecting employees, departments, and time periods. And for the time period here, we can introduce again the from and to attributes. And so here, for the same combination of employee and department, we might actually have multiple time periods during which the employee worked for the department, right? So that is somewhat subtle points, but when creating a database, then those points actually matter a lot, and you have to be very careful that all the constraints that you want to represent and all the things that you want to be able to express can be expressed using the database model that you are choosing. Is there any questions on this? Okay, that's an interesting proposition. So the proposition is that we might also consider using aggregation here. So we have the employee and the department, that is the works for relationship. And now we could associate this via aggregation with the time period. I assume that's the proposition here. So a priori in this context, you could also use aggregation. I imagine that you, via aggregation, that the works for relationship has a time period. So in this scenario, you could also model it via aggregation. I assume that you would connect the works for relationship to a time period entity again, perhaps, which would also be possible. I'm not sure whether it gives you additional things that you can express in that way that you cannot express in this way. So with the corresponding constraints, I think you would get something which is close to what we are modeling here. So the answer is yes, you can use aggregation. And the question is, okay, so you want to make sure that the works for relationship has a time period. So in this representation, that is actually ensured because each of those works for relationships must connect one employee, one department, and one time period. So with this representation, you essentially ensure that we mark down a time period for the employment. All right. And all right, and then there is another question. How can you make some of these relationships more explicit? What about when things aren't as clear? Say if an employee works for another employee in the department is a property of where they work. Okay, so in general, so I mean, what we ultimately want to do with those entity relationship diagrams is that we essentially want to formulate those SQL create commands for different tables in order to create a database schema into which you can insert your data. So it is true that it can sometimes be challenging to consider all possible situations in advance. Often those database schemata, they need to evolve, they need to get changed over time in order to either extend them or in order to represent changes that a company is going through, for instance, which impact the data model that they want to use. But I mean, in principle, so basically, I mean, if you want to work with a database, then you have to make a decision about which schema you want to use. You can, of course, adapt that decision over time, but you need to decide which tables to create. So entity relationship diagrams, they help you to make that decision. If your question refers to whether it can be difficult to integrate all possible situations in those entity relationship diagrams, I agree with you. That can be challenging. But for sure, if you want to work with a database, I mean, you have to decide on the schema that you want to use in your database. So even though it can be challenging, there is no alternative, basically. So, okay, all right, yeah, but great question. So, I mean, I think in many of those cases, it is difficult to come up with a good entity relationship diagram. It's also an iterative process. You make a first draft, then you realize, oh, there's a situation that I didn't consider and which I cannot represent with this entity relationship diagram. Then you refine it, and you do this a couple of times until you come to something that you like. So it is challenging, but I mean, we have to decide on some structure for the database. All right, great questions. Now let's discuss a different scenario. So here we are modeling the manager-managers project relationship. And here we have a budget. And let's say this budget is meant to represent a budget that one specific manager has in order to manage all of that person's projects. Same question as before. Can anyone tell me what is wrong with this representation? Okay, so there's some information that is not represented in this diagram. I mentioned that the budget that is specific to one specific manager, but here it doesn't say how that budget is partitioned across different projects. Yes, exactly. One manager could manage multiple projects. Yes. So I think, yes. So this is all aiming at the right thing. So the problem is this budget relationship. And very correct here, the point that one manager could manage multiple projects. And in that case, first of all, we are missing information. So because we don't represent how the budget is partitioned across multiple projects. And also we introduce some redundancy because, I mean, here we essentially model something where we would need to store this budget for each manager project combination, right? I mean, those attributes of the relationships, they're essentially stored for each combination of the entities that are involved in the relationship. And if the VJ only depends on the manager, but not on the project, then this representation is redundant. So a better way to store that would be, for instance, this one over here. So here we represent managers as a specific type of employees that are associated with a VJ. So here the attribute is associated with the entity, not with the manager's relationship. And that is more intuitive and avoids redundancies here. Still, there would be probably, it would be good to introduce the specific budget for each project and make this an attribute of the manager's relationship. So that was a great point here. So here we have only taken care of the redundancy. So those are subtleties, but nevertheless, in practice, it would be very important to make sure that you choose the right representation. All right. Now, in order to get the hang of it a little bit, I wanted to make a little exercise. It gives you a couple of minutes. Try to draw an entity relationship diagram which describes the following situation. So we are modeling customers that have a unique ID in the name. We have orders that are associated with customers, and each order consists of at least one item. Those items, they have also an ID, which is unique, a name, and a price. So I give you a little bit of time to draw one of those entity relationship diagrams for this situation. So just take a sheet of paper perhaps and try to model that. If there's any more questions about entity relationship diagrams, I'm happy to answer them here. No questions on entity relationship diagrams. Give you one more minute, then I'm gonna show you the solution. Right, let's quickly have a look. So here we introduce an entity type for the customers with the associated attributes, which is ID and name. ID is marked as a key by underlining it. Then we have a connection between customers and orders. And we also have an association between orders and the items. Items have the attributes that are mentioned in the description. And here the orders are connected to the items via a participation constraint. You have the SIG line over there, which means that each order must consist of at least one item, otherwise it is not a proper order. And since the part of a relationship connects specific orders and items, we might also have multiple items of the same type. And in order to model that situation, we introduce the number attribute. Also between order and customer, logically an order needs to belong to one customer, exactly one customer. And this is what the constraint here with the SIG line and the arrow is expressing. And here there's a question. Is there a way to do this with order being a relationship instead of an entity? Why not? So maybe one high level remark. So in general, there's always many possibilities to describe the same situation with entity relationship diagrams. So if there is a different solution from this one, it does not at all mean that that solution cannot be correct. So like when writing SQL queries, there's always many different ways to express the same query, or here express the same situation, and all of them can be correct. So modeling order as a relationship, I assume that would be a relationship connecting the customer with items. Okay. And then, yeah, I think you can also make that work. So you would have to express that each item needs to be associated with an order. Yeah, so, okay, I can see that. It depends on the specifics, but I believe that there's also ways to model this when connecting customers and items with an order relationship. And number, that is an attribute of the part of a relationship. So here, those relationships essentially can contain information about each order and item combination at most once. So if we want to model the case that we have multiple instances of an item in the same order, then the way to model that is to introduce an attribute which captures the number of items for each order item combination. And so this is what the diagram is essentially doing. So that is essentially the number of times that each item appears in an order. All right. So now we have learned the formalism to represent the database structure at the high level of abstraction, those entity relationship diagrams. Ultimately, our goal is to translate them into SQL commands for creating the associated tables. So in the following, we're going to see how we can translate those entity relationship diagrams into actual relations. And then for those relations, it is relatively natural to formulate corresponding SQL commands for creating those relations. So in order to represent those entity types, which appear as rectangles in the diagrams, we introduce a relation such that one entity corresponds to one row in that relation. And different properties of an entity are represented as columns of that relation. The underlined attributes, they become the primary key. For relationships, we can also introduce relations, which essentially contain one row for each combination of connected entities. So the columns of that relation representing the relationship, the diamond in the entity relationship diagram, would essentially contain the primary keys of all the entities that the relationship connects. And then one row would represent the relationship between specific entities. If the relationship is associated with additional attributes, then those attributes become additional columns in that relation. Let's make things a little bit more concrete by an example. So here we have a relationship between students and courses. We are expressing that each student has exactly one favorite course. We have the net ID and the student name as attributes of the student, and we have the course ID and the course name as attributes of the course. And also this favorite relationship is associated with one attribute since. So for a specific combination of a student in a course, this attribute gives us the time starting from which the course became the favorite of the student. And now we can chat, and now we can express, we can translate this entity relationship diagram into relations as you see here in red. So the student entities, they get translated into a relation student, which has columns for the net ID and the student name. And the net ID is the key column, which when representing relations, we always represent that as well by underlining the corresponding column. On the other side, we have a relation, a course, which stores the courses, and again has course ID as a key column. And then the relationship between the students and the courses is expressed by this favorite relation, which has the net ID and the course ID as a primary key columns. So here this is essentially the combination of the primary keys of all involved entities. And also it has this additional column in order to store the since attribute. So here that is one generic way in which we can model relationships, how we can translate them into actual relations. Here we can just add one corresponding relation, and the primary key columns of that relation just collect the primary key columns from all the involved entities. So we can store something about each possible combination of students and courses here. And then after I have those relations, it is relatively natural to formulate corresponding crate table statements in SQL in order to actually get the database that this diagram is describing. Now, I can do better than that depending on the type of the relationship. I mean, specifically for binary relationship, we have a couple of different types. We distinguish the type of relationship based on the constraints that I have, and say that I can either have a binary relationship of type many, which essentially connects an arbitrary number of entities to an arbitrary number of entities on the other side. I can have a many-to-one relationship, which means that entities on one side can only appear once in this relationship. And I can have a one-to-one relationship, which means that entities on both sides of the relationship can only appear once within it. So I mean, all of those different relationship types, they use the at most one constraint that we have seen before, which is represented as an arrow in the entity relationship diagram. And this is a quick overview of how I can model relationships of different types. The many-to-many relationship is the most generic type of relationship because it doesn't impose any constraints on how often entities can be in that relationship. So here the only way to represent that is the generic way where we introduce one new relation in order to represent that relationship. And that is the way which we have already seen before. For the many-to-one relationship, we can essentially avoid introducing a new separate relation in order to model the relationship. Instead, we can merge the relationship and represent it as additional columns of the relation representing entities on the one side. If I have a one-on-one relationship, then I can even simplify things further and represent both entities involved in the relationship together with the relationship itself in one single relation, in one single table. Now, that is a little bit abstract, so let's make it more concrete by an example here. So here we have the same example as before. And now in this case, we have the constraint that the student can only have one specific course as a favorite. So here what we can do is that, so here what we can do is that we introduce a new column in the student relation which points at the favorite course. So we have here again the net ID column, the student name column, but now we have essentially merged columns that we have put into a separate relation before. Now we have merged them into the student relation. So here we have the favorite, which is essentially pointing to the course ID of the favorite course. And then we also have the since column, which represents the point in time at which the course became the favorite. And we can only do that because we know that for each student, there can be at most, or in this case, exactly one favorite course. Because of that, we know that we can just put all of that information into the same row which describes the corresponding student. If a student could have multiple favorite courses, then the system would not work. In that case, I would need to introduce a new separate relation in order to represent this relationship. And here we have another example. So here we have the connection between lecturers and courses, capturing which lecturers teach which courses. And here we have even more constraints. So each lecturer can appear at most once in this relationship, and each course can appear at most once in this relationship. So there's this one-to-one connection between lecturers and courses, and therefore I could merge everything together into one table where I simply represent the lecturers and the courses, and together with all the associated attributes. So those are a few ways in which I can simplify the translation from the entity relationship diagram into relations and ultimately SQL code. The assumption here is that it is typically better to have less relations in your database, less tables in your database, because then in order to combine information from multiple sources, you might have to execute less joins. It's a simplifying assumption, but nevertheless, in practice, you typically try to exploit those constraints in order to prune down the number of tables that you need to generate. All right, now we are at the end of the time frame for the lecture. The next time we're gonna continue discussing about the translation from entity relationship diagrams into SQL. And we're also gonna start discussing about how we can optimize an initial draft of our schema. Have a nice weekend, and then I see you again next week.